This is Unit 1, Our Place in the Universe, Day 2. We will be dealing with Learning Target 1.A, which deals with cosmology. Cosmology is the study of the cosmos, or everything out in outer space. We'll be able to explain cosmology, including our Big Bang Theory, describe the expansion of the universe using the electromagnetic spectrum, specifically dealing with our redshift, and then compare and contrast the Big Bang Theory and solar nebular theory. We'll also cover Learning Target 1B, which deals with our galaxies, and we'll be able to explain the potential origin and role of ultramassive black holes in the center of our galaxies and examine the classification of different galaxies. In order to understand everything that we're going to talk about, we need to understand space radiation. Radiation is just energy that is moving in waves. All objects in outer space emit wavelengths of radiation that are part of what we call our electromagnetic spectrum. This is where we classify all of our waves according to their wavelength, or how spread out this line is. Down here we can see our radio waves. This is what allows us to listen to the radio. We have our microwaves. This is what we use to cook our food. We have our infrared waves. These are the ones that we can feel heat coming off of something. We call it radiant heat. Sometimes we use special technology to see heat signatures being given off. It brings us to our visible light waves. These are the ones that our eyes and our brains use for us to create an image of everything around us. Just below that, we have our ultraviolet rays. These are the ones that we are concerned about when we're sitting out in the sun and we put on sunscreen to block those rays from hurting our skin. We have our X-rays that are used to take our medical X-rays. And we have gamma rays. These are given off by radioactive sources. Now, using our electromagnetic spectrum, it can tell us what elements make up stars and nebulas, our clouds of dust and gas out in outer space. Each element gives off its own fingerprint of light. Spectroscopy is a technique in which visible light is examined to determine an object's composition, temperature, motion, and density. If we look at the image over here, these are a few of things that we can see using spectroscopy. So if I look at a star out in a galaxy far, far away, and the light coming back gives off a specific fingerprint, we can tell what elements are making up that star. For instance, this is hydrogen, this is helium, and you can see there are a bunch of different, they are all very different from each other. The electromagnetic spectrum also tells us if objects are moving towards or away from us. This is using what we call the Doppler effect. The Doppler effect is a change in wavelength as emitting object moves closer or farther from the observer. If we look in this image here, this is our police car. He has his siren on. It's giving off sound waves. That's what these black lines here are representing. So our police car is moving in this direction towards the person standing at point A. Now, as he's moving in that direction with his siren on, the sound waves are getting bunched up closer and closer together. That means the person standing here at point A will hear a higher pitch on that siren. As he's moving away from the person at point B, those sound waves are getting more and more spread out. That means the person standing here at point B will hear a lower pitch on that siren. We've all heard this before. Think when you're sitting in the car, you hear a car with its horn on, he's approaching from behind. Those sound waves get all bunched up and it sounds a little bit higher. And then as he passes, the sound of that horn is going to change and it's going to sound a little bit lower. Now the same exact thing happens with light waves. With our light waves, they get shifted either more to the red color spectrum, so we call it red shifted, or they get shifted more to the blue side of our spectrum, or blue shifted. Objects moving away from us will be red shifted because the wavelength is getting more spread out. Objects moving toward us will appear blue shifted because the waves get more bunched up. Now, using this, Edwin Hubble and other astronomers saw that the galaxies were all red shifted, which means they're all moving away from each other. This means that our universe is expanding. This expanding universe is our best evidence for our Big Bang theory. Our Big Bang theory states the universe began in a very hot, dense state that expanded and eventually condensed into individual galaxies. Formation of galaxies is still happening. According to the Big Bang theory, the universe began expanding approximately 15 billion years ago and has created all of the matter that is out in the universe. This brings us to our solar nebula theory. Planets were formed in a spinning condensing cloud of hot gas and dust. Dense concentrations of gas are at the center of the disk, eventually become the sun or a star. Planets are formed around the same time as the sun from all of the matter left around the center. So when we look at the stages of our solar nebula theory, everything starts as a nebula, a cloud of dust and gas. It starts to collapse. In other words, gravity starts to take over and everything is going to pull into the center. As it's pulling into the center, it's going to start spinning. Just like when you open the drain in a bathtub, all the water pulls to the center of that drain, it's going to start spinning. As it's spinning, it starts to flatten and form rings. Now you can see at the very center you have what we call a protostar. This is what will become the star at the center of the solar system. After it's flattened out, you get more clear rings or condensation. In other words, our more dense matter is going to stay in rings right around the center of our protostar. And our less dense material, our gases, are going to form rings around the outside of what will become our solar system. The final stage is what we call accretion. Accretion is just where you have a bunch of material sticking together and building up larger and larger objects. So there we see what's going to become our sun, and we have accretion of planets happening all around the outside. When we're measuring distances out to galaxies in the universe, we use what's called a light year. A light year is the distance light travels in 1 year. It's around 10 trillion kilometers. Again, a light year is the distance light travels in 1 year. When we look at our galaxies, all a galaxy is a huge rotating disk of stars, dust, gas, and other debris that's all held together with gravity. Usually at the center of our galaxy, we're going to find a black hole. Around that, we're going to have billions of stars. At this point in time, it's estimated that there's about 100 billion galaxies in the universe. Now our black holes, they're called black because they are so dense, the gravity is so great around these points where the light cannot even escape gravity's hold. In other words, even light, even if it tries to leave, it gets sucked back in. They may continue to grow by absorbing mass from everything around it, Eventually, they're going to form what we call supermassive black holes by accumulating mass and merging with other black holes. And supermassive black holes are at the center of most galaxies. We classify our galaxies based on shape. We have three basic types. We have our spiral galaxy. We have our elliptical galaxy. Ellipses are basically ovals. And then we have our irregular galaxies, which don't basically fit into either the spiral or elliptical category. Our spiral galaxies, the central core is going to be a supermassive black hole. Our areas of stars resembling arms coming off the central core. Our youngest stars are in the arms, and our oldest are near the central bulge. And when we're talking about the central bulge, this is the core. What's at the center? This is where all of our old stars are. And then you see the arms coming off. That's where our young stars are going to be. Just like in this one, this is our central bulge where all of our old stars are, and you can see the arms coming off where all of our younger stars are going to be. Our elliptical galaxies, or oval-shaped galaxies. The central core, right here, there's going to be a supermassive black hole. There's no arms, and the stars are going to be more spread out evenly around the core. Mostly made of old stars. We're not going to see a lot of new star formation in elliptical galaxies. The type of galaxy is our irregular galaxy. In other words, it can't be classified as either a spiral or elliptical. It has a weird shape. There's no central core, there's no arms or organized shape, and it tends to be smaller than our spiral and elliptical galaxies. The Milky Way, home sweet home. Now, if you've ever had a chance to go out to an area that's far away from city lights, you're going to look up and you're going to see this wonderful band up in the night sky. This is because we are inside of a disc-shaped structure. So when we look out, we can see one of the outer arms of the Milky Way. It's classified as a barred spiral galaxy. It's classified as barred spiral because you can see here in the center, the central core is more bar-shaped than circular. Okay? It's estimated to contain 100 to 400 billion stars. Now, a lot of those stars have solar systems around them with at least 100 billion planets. Our galactic center is most likely a supermassive black hole that we've named Sagittarius A.